Hi, Assalamualaikum. My name is Hazani Humaira binti Hairul Isam, and this is my final year project video about root optimization for printed circuit board drilling machines using a bio-inspired heterogeneous ant colony algorithm. So this is a printed circuit board or PCB. It is inside almost every electronic devices that you use every day. Your phone, your laptop, your earphones, it is in all of this. So look closely at the board. You can see hundreds of tiny holes drilled into it. And these holes are where the electronic components get connected. Now, what if I told you that the order of the machine drills these holes actually matters? This is what the project is about. This is a real CNC PCB drilling machine in action. Watch how the drill heads moves across the board, visiting hole after hole. It looks fast, but is it actually taking the most efficient route? Or is it making unnecessary movements, wasting time and energy with every single board that it drills? So when a factory produces thousands of boards every day, even small inefficiencies add up to a lot of wasted costs. So here's the problem. A single PCB can have up to 3038 drilling holes. The machine needs to visit every hole and return to where it started using the shortest possible route. So this is a famous computer science problem called a traveling salesman problem or TSP, and it is classified as an NP hard, which means that the number of possible routes is so enormous that no computer can check all of them. For 3038 holes, the combinations are basically infinite. So we need a smart algorithm to find a good solution. Now existing algorithms called ACO, ant colony optimization, already do this, but they have a limitation. Every ant in the colony uses the exact same settings, and they all will think the same way. So this limits to how well the colony can explore different routes. My solution is called h-MMAS, Heterogeneous Max-Min Ant System, and the key idea is simple: give every ant its own unique personality. Let me quickly explain how it works. So ACO is inspired by real ants. When an ant looks for food, they will leave a chemical trail called pheromone. The shorter, better path will collect more pheromone over time. So more ants will follow them and the colony will eventually find the best route. In the standard MMAS, which is the strongest version of ACO, all the ants uses the same fixed alpha and beta values. The alpha controls how much an ant follows the pheromone and the beta controls how much an ant prefers the nearby nodes. So every ant will behave identically. In the h-MMAS, I add one key change, which is each ant will get its own random alpha between 0 and 2 and its own random beta between 1 and 3. So, in a colony of 442 ants, some ants are explorers that ignore the pheromone and find a new path, some are followers that strongly follow the best known trail, some are greedy and always pick the nearest hole, and some are more flexible. All of them are working together at the same time. That is the power of heterogeneity. Okay, now let's see the algorithm actually running. So this is EL51, a benchmark dataset with 51 cities, and I am using this one to demonstrate because it completes quickly and the result is easy to see. So right now the virtual ants are building routes. Each ant will visit all the 51 nodes and return to the start. So after every iteration, the best route found so far gets recorded. So after the iterations are finished, we can see here which is the diversity curve, the standard deviation of all ant costs. It starts high when ants are actively exploring different paths and then gradually settles as the colony agrees on a good solution. Next, we can see the convergence curve, where it is dropping. The algorithm is finding better and better routes as the ant learn from each other through the pheromone. And then we can see the best tour path. Now each dot is a city and each line is the route. We can see here it is a clean path with minimal crossing. And after that, we can see the histogram graph where it is distributed evenly, which means that the heterogeneous is applied. So the non-optimal solution for EL51 is 426. h-MMAS found 429, and that is only 0.7% away from the perfect solution. So to make sure the results are reliable, I ran each algorithm 3 independent times with a different random seeds. So as you can see in the table here, for the non-PCB datasets, Berlin 52 achieved exactly 0% gap from the optimal solution, which is a perfect solution found. Crow A100 also hit exact optimal in one of the runs. For the PCB instances, like PCB 442 received a 2.38% gap from the optimal, A280 received a 12.68% gap, PCB 1173 received 6.67% gap, and all of these are pretty close percentage through from the optimal solution, which I think is a very good result. Now here's the full comparison. h-MMAS against MMAS, ACO, and nearest neighbor across all the 7 datasets. Lower gap percentage means better. On every single PCB dataset, we can see that the h-MMAS with a candidate list gives the best result. PCB 442 at 1.93%, PCB 1173 at 6.3%, A280 at 10.78%, compared to PCB 1173, the h-MMAS 6.3% versus the ACO at 33.84%. Now that's more than 5 times better. We can see that the heterogeneous approach consistently outperforms using a fixed identical settings for all the ends. So beyond the algorithm itself, this project connects to real sustainability goals. Shorter routes means less machine movement, less electricity per board. Less unnecessary movements means the drill bits last longer, which is less waste. And the less energy in manufacturing means a lower carbon emissions. So small optimization, real world impact. After each run, here are the results we will see. First is the histogram graph, the best toolpath graph, the convergence graph, and the standard deviation graph. As you can see in the slide here, at the top is the h-MMAS results. And the lower left here, we can see the MMAS result. Besides it is the ACO result, and finally, the lower right side of the slide is the nearest neighbor results. So that's h-MMAS, a heterogeneous ant colony algorithm that makes PCB drilling machines smarter. Tested on 7 benchmark datasets, best result exact optimal on Berlin's 52 and Crow A100. And on the main PCB datasets, just 1.93% from perfect. So for future work, I plan to validate this on a real physical CNC drilling machine, the Boomguard CCD/2/ATC, to measure the actual drilling time savings in the real world. Thank you for watching.